starting and check whether it works well or not. Right, does it go well? And we're gonna use this one. Belakang. Right, okay, in that one. Right here, this is the okay, that's matter. Left sharps monitor. This one, right? Beyond keep on. This is this one. Yes, in this one should the right sharp screen. It should be right there in TV1 or TV2. It's something like that. And there's nothing more, right? Okay. And now we're gonna monitor the 55 at the same time. Okay. It 40, right? Yes. What else? The microphone, right? Microphone. Okay. Right here. Okay. เพจ time มาแล้วนะครับ and we will take a look at the stream health, right? Next thing is to go. That works fine. Let's go. Leave it like that. Like this. Yes. Now we yes. Okay. Good morning, everyone. I'm gonna send the new version of chapter 7 to this iPad, right? Because many things has been updated. In we need to change the microphone here. Two people is in data in this one and section, and we open a new version of the file, and just we import something in lecture. No, in this one, and the 7th chapter, right? this one for M604 and actually it's 20. Okay. Yes, for you in M604, right? We alive somehow the calculation of the beta, right? The beta decay, and yes, we reach the. I'm not sure whether you could hear well or not. Let me check the sound. No, there is no sound in Zoom at all. Test one. Okay, มาแล้วเสียง Test 1, 2, 3. Yes, we arrive at this example for M604. Okay, most of you have the just written your name in the YouTube channel. Oh. No, my God. What? Oh. Why? Okay. Yes, I'm gonna check whether some of you try to join. Oh, it's she. My one. So now, oh, I don't understand why it goes like this. Okay, yes, this is the beta decay and oh. I don't understand why. Okay. HDMI. Okay. And here too. HDMI. Okay. For us beta decay calculation, right? We are gonna find the released energy for the beta decay. Just it's the conversion from carbon to be nitrogen 14, right? It's the 604 นะครับรู้สึกผ่านทุกคนนะครับเรื่องสอบซ่อมนะครับแล้วก็เขาเรียกว่าอะไร605นะปานทัศน์ก็ผมเช็คตอนที่2แล้วก็ผ่านนะครับก็เหลือแค่พวกงานการบ้านนะครับก็เราก็จะหมดเทอมเหลือสอบปลายภาคกันได้อะไรอย่างเงี้ยครับ Okay, all right. Yes, let's go further for us in this problem. We consider carbon 14, right? Beta decay. Carbon 14 has the atomic mass like this, right? 14.003. Okay, it's not exactly 14. Okay, because this is the atomic mass, but if you say mass number is going to be exactly 14, right? Integer version. And for atomic mass, it has a little bit deviation from the exact 14, and the nitrogen 14 too. Even it has also 14 nucleons, but the atomic mass is quite different. It's 14.003 and 0.74, right? Yes, in order to see the conversion here, you could see that the exact transformation is given in equation 56, which is the beta minus the emission, right? It's an electron emission actually. Okay, and but in order to do the computation, we are going to use the complete atom that has มีปกติชัยสิทธิ์จะเข้านะมีใครจะเข้าไหมครับไม่มีนะ okay we will consider the complete version of the whole atom, right? Because the value they have provided here is the atomic mass, the mass of the whole atom. So it's better if we add 6 electrons to this, and we add 6 or also 6 electrons to the right hand side, and we have one more electron that is the emission in the topic of beta decay, right? This one, okay, beta minus process. And yes, of course, we are going to consider the released energy. So the one that we could see is the excess mass, right? The mass that is greater than the input side. So you could see that the output that has mainly the nucleus of the nitrogen 14 074, and this one 242, right? Carbon has more mass, right? It means the mass is reduced, the mass disappear. Not span excess, I'm sorry for that. The mass in the left hand side in the input is greater than the mass in the output. So 242 is greater than 74, 242 here. And so there will be mass loss, okay, or mass deficit, you can say. And the mass will be converted to the energy, and the relation between the mass and the energy is given by the Albert-Einstein famous relation. And yes, we make the subtraction, right? This one, right? The mass at the inputs, the mass at the input side, okay, and the mass in the output side in the beta decay process. And you can also substitute the mass in SI system, but it's not recommended because it's too complicated. You just use the atomic mass unit scale. Okay, it's better, it's easier, and you just use the 931. Okay, 931.5. 931.5 means the result from the conversion. Okay, it's quite simple, and you don't have to worry. Just make the multiplication only. All right. So the next step is that you find the difference of the mass in so OBS, right? Oh no, we move to another channel. So, zoom to YouTube. We are going to observe the zoom to YouTube. Okay, in zoom to YouTube, ประภาวิทย์ประธานินทร์พิสุทธิ์ปัญญะธนนัทวีรพัฒน์ครับ in OBS some people are there, right? Okay, and the next one is we find the difference of the mass between the input side carbon 14 and the output side the nitrogen 14. And one of the neutron has been converted to be proton. So we have one more proton. And yeah, neutron will emit also one more electron. That's why we have one more electron at the output. But we neglect the mass of the electron, okay? because the mass in the nucleus is more significant. We multiply the mass difference or the mass loss by 931, which is the result of C square mega electron volt per atomic mass unit, and we have here the mass difference already in the atomic mass unit, so it's convenient. The unit will cancel each other, so the outcome will be expressed in mega electron volt easily. It's 0.15, okay, for one process of the carbon to nitrogen conversion, okay, and this will serve as the calculation in radiocarbon dating too, okay. The radiocarbon dating is a technique to determine how long an organism will last or has started to die. Okay, we will talk about that later. And here is the example, right, for the carbon 14 to become nitrogen 14. Okay, the next one is another process that is still beta minus decay. Okay, it emits electron, right? So it's taken from the book number 1. This one is taken from also book number 1 in example 29.4. This is exercise 29.4. Well, we consider the potassium 40. Potassium 40 is an isotope of the potassium, and the mass is not exactly 40, right? The atomic mass of potassium 40 is 39.9 blah blah blah. Okay, very close to 40 actually, but this is the result from the actual measurement. I cannot. We need to rely on, and we cannot say no to that. And the next one is the calcium 40. Okay, it's the next element after potassium, right? Once it has one more proton, okay, and this one has 21 neutrons, and this one has only 20 neutrons. So one proton from the potassium is converted to be proton, and of course during this conversion, the neutron will emit electron. Okay, but I would say these two problems are actually still invalid because we will talk about one missing detail later. Okay, they are still incorrect, but okay, but we go ahead with that. I calculate the released energy of the beta decay because it emits the electron, right? Beta minus means electron, right? So it's gonna emit the electron, but in order to use these two values, this is the values measured by chemists, okay, the people in chemistry, they measure the complete atoms, okay, with together with the electron, associated electron. They didn't measure the nucleus, okay, without in ionizing state. They measure it in complete atom. So in order to use this value, we have to add electrons so that the nucleus become normal. Okay, it's not ionized. We add 19 electron to the left hand side. We add also 19 electrons to the right hand side. But since we have already one in advance, okay, one electron in advance, we need to have 20 electrons. So now the equation is valid for this value because this is the whole complete atom for potassium 40, and here is the complete version of the calcium 40. We could use this one, okay, and this one is these two values are captured from the measurement table. So you can see also in the appendix of several books, but the values might be different from each other from different sources. Okay, but they are very close in the first 3 digits. Okay. Yes. Again, the release energy could be found from the famous Albert-Einstein relation EMC square. But for us in this topic, we are gonna use it in the simple version, right? It's 931.5 mega electron volt per atomic mass unit, right? Yes, that's the situation we're gonna use. We usually use, okay, this energy can be calculated from the mass difference between the initial particle, which is potassium 40, and the resultant particles, which is calcium 40. And yes, we make the subtraction, the mass difference, and yeah, you could see that this ends up with 3999, and this one ends up with 2591. So 3,000, almost 4,000 is greater than 2,600, right? So the mass at the input side is greater than the mass at the output side. So it means there is mass lost, and that mass lost is converted to become the released energy, or you can say it's liberated energy. Okay, it's up to you. What word do you want to say? Okay, in several books they use different terms, but it doesn't matter for us. Yeah, we calculate the mass difference, make a subtraction of these two numbers. Okay, it's very minor, but once you multiply it by almost 1,000 here, which is the result from EMC square by Albert-Einstein relation, we're gonna get 1.3 mega electron volt as the outcome. Okay, so it's considerable, right? But it's not popular for a human to use this process to get the energy, because there are some more processes that can bring us more energy. We will see it later in the next topics. Okay, let's compare for a small nucleus like carbon 14 or nitrogen 14. We got the energy on 0.1516 mega electron volt. But once we go to the bigger nucleus like potassium 40 to calcium 40 or something, the number of neutrons changes from 14 to 40, we get the release the energy on 1.3 mega electron volts. So you could say it's almost 10 times greater than the 14 nucleons here. Okay, once we consider 14 nucleons, we got more energy. Okay, that's the energy you can get from the beta minus released process. Then an electron is the outcome, is the product from this process. All right, let's move to the next one. Beta minus decay, the electron, right? And beta minus is denoted by -1, 0, because the number of proton is negative. It's electron, right? It's in the opposite way to the proton, and there is no nucleon at all because it's a tiny particle. It's lepton, right? It's lepton. It's not boson, right? Okay, recoiling nucleus. So we have one more proton. But the number of nucleon is the same. Okay, there is conservation of momentum and energy in this process, and usually, but required to have a definite energy. But from the calculation in the two previous examples, as you have seen, both energy and angular momentum were not conserved in the beta decay, and beta minus particles are found to have continuous spectrum of energy. So what's the problem then? Usually we would get the discrete value, right, from what we have calculated here. But from the measurement, the energy from the electron is continuous. It's not discrete. Like if we get certain value like this, as in the alpha particle, we got the, sorry, let me use the hand. In the alpha particle, we got a discrete energy because we compute, we have seen the least energy as a discrete value, like same as in alpha process, right? But what is the reason why we also get a discrete value in the calculation, in the calculation? Oh, sorry. In the calculation, we got also the released energy in discrete number. But from the experiment, physics is quite strict. We have to compare it to the actual measurement, and but the apparent spectrum is continuous. So what is the reason behind that? The observed energy of beta particles are continuous, have all value up to maximum value. So is the measurement wrong or anything else? No. There should be something missing in this beta decay processes. Okay. Then the people try to observe what is missing inside the beta process. Okay. And one of the impact idea emerges as follow. Okay, two people. The first person is the well-known one. You may have ever heard his name. It's Wolfgang Pauli. Okay, Wolfgang Pauli is the person who pay attention to this incorrect outcome. Okay, why the power spectrum is not discrete as in the alpha decay process. Okay, and it turns in the following way. Wolfgang Pauli, beta decay result in daughter particle with variety of possible kinetic energy. As you can see here, it's continuous. So it would not be only electron. The energy we got here would not be due to the electron only. So in 1930, Wolfgang Pauli, okay, Pauli has released or has given the exclusion principle, right? He said not only to electron, okay. In the previous chapter, he said the Wolfgang Pauli exclusion principle for electron cannot share the same quantum number, right? But also valid for the any particle. It cannot share the same quantum number apart from the electron. Okay, it's like a boson and so on. Yeah. Okay, I'm not sure whether there is anyone who want to join the Zoom or not. Usually, Shayasit is going to attend the Zoom classroom, right? Okay. Yeah, because there is something missing, something is wrong. Is that the measurement doesn't correspond to our calculation here. So Wolfgang Pauli tried to investigate it in 1930, and he said that there should be a third particle which doesn't appear in. Oh, let me open another one. It's more convenient to scroll in, scroll up and scroll down in 7. Today is 21. Okay. In 55, in this process, a general form of the beta decay, there should be a missing particle on the right-hand side. We know before we have the input at the starting side. In the starting side, we have the mother nucleus, and it's decomposed into another nucleus, and 1 neutron is converted to proton, and the electron is emitted from the nucleus. But according to the measurement, the output is not discrete. The power spectrum of the light of the four emitted beta particle are not continuous. So there should be something wrong. Okay, and Wolfgang Pauli said there should be another particle on the right-hand side. apart from electron or the beta particle. This particle should be electrically neutral because we have already seen the balance of the charge between left side and right side. Okay, proton is created and electron is created, so they cancel each other in terms of electric charge. So an additional particle here should not break the charge conservation. So it means this particle, the new one which is missing here, should be neutral. It has no charge value at all. So it should be electrically neutral. Okay, it should have no charge. So the conservation law would really serve. And later, Fermi, Fermi is quite well known. So Fermion comes from his surname, right? And he builds, or he was also the person who built up so many things inside this. Okay. Next one we consider in 1935. In 1955. After Wolfgang Pauli suggests that there should be an additional particle, but I don't know, maybe he has passed it when he didn't have time at that time. Enrico Fermi said these particles should be called, because he lives in Italy, right? So he uses his language, Italian, every day. He called this missing particle suggested by Wolfgang Pauli as neutrino. Okay, it's an Italian word. Neutrino comes from the Latin root, which is neutral, right? It has no charge. And neutrino, in the sense of Italian, means it's a little neutral one. Okay, a particle that is neutral and little, so it's very, very small compared to electron. Okay, that's the first idea. And once these two big people, two big persons suggest this, in 20 years later, or approximately 20 years later, someone has some people have tried to observe this, and they found it accidentally in the reaction nuclear process. It's called nuclear reactor. It's a device to change the nucleus or the nuclei of big atom. Okay, those researchers are Clyde Cowan and Frederick Linus, recorded the antineutrinos, which is the particle missing here in 55. Today, this particle, which is known before by Enrico Fermi as neutrino, is known as antineutrino, because neutrino will take place with beta plus. Antineutrino will take place together with electron. Okay, so the equation 55 is no longer valid, and they add another. 54 or 55. 54 is the fundamental one. 55 is general expression for any element, right? But they come from the same root. So 54 or 55 are no longer valid. They add another particle to the right hand side, but the information of this particle is still missing. It's not completely well investigated at the moment. Okay, maybe in your generation it might be clear about the information of this particle, but maybe it's not for my lifetime. Okay, I was born before you. Okay, instead of 55, there should be another particle, and it has, you could see here the notation. There is no proton, there is no value for the nucleon, right? So it's a tiny particle that doesn't exist at the nucleus of any nuclei. Okay, it's nu, okay, nu, nu, the Greek letter with bar means anti particle. With a subscript E, it takes place corresponding to the electron. So it's called electron antineutrino. Okay, it's take place together with electron. But this particle is unfortunately hard to detect because it has very, very little mass and it has no it has no charge. Once the particle has no charge, it is very hard to detect because if it has charge, we just leave it. When it moves through the magnetic field, it's gonna rotate in a circular way, right? And if we can measure the circle of its propagation, we could find the we could find the radius and we could find the velocity of this particle. Once it is very, very tiny, its mass is very, very small. Even today, we cannot find the exact mass of this electron antineutrino. So it's very hard to detect. It has no action to any other stuff because it's neutral. It has no charge. So the information of this one is still missing, and the physicists are still trying to get some information about this. Unfortunately, my lifetime, I cannot deliver the actual information to you for this particle. Okay. Yeah, let's make the conclusion in the better view for the beta decay process. Once you know that there is a missing particle in 54, 55, or 57 for the beta plus decay process, we can summarize in a picture like this. Okay, let's take a look first at the beta plus decay. You have the proton. Proton is made of 3 quarks, right? If you can still remember the story in the previous chapter, proton consists of 3 quarks. 2 of the quarks are up quarks, and 1 of the quark is down quark, and it is attached. They are attached to each other by using the particle which are known as gluons, right? Gluons come from the word glue, which means these particles try to attach these 3 metals together to form of beta, to form of the proton. Actually, there are some more particles apart from gluon, but you need to go to the bachelor degree level. Okay, you will get some more information. But for us in high school, it's already in a very deep detail once you know the up quarks and the down quark form of the proton. And the neutron consists of 2 down quarks instead of the up quarks, and 1 up quark here. Okay, and as you know, the this one has 2 by 3. I think yes, this one is negative 1 by 3, and once you combine, the charge is going to be 1. Okay, 2 by 3 plus 2 by 3 minus 1 by 3, you get 1 by 1, which is the charge calculation for the proton. And here you have negative 1 by 3 and 2 by 3, so it cancels each other, so neutron has no charge. จำได้ไหมครับบทที่แล้วนะครับโอเค1 up quark is equal to through by still with 1 up quark correspond. Oh my god, what happens? Okay, 1 up quark correspond to 2 by 3 charge n. You have 2 quark, right? You get 2 by 3 and 2 by 3, and 1 down quark correspond to minus 1 down quark correspond to 1 minus 1 by 3, 1/3 charge. So if you combine these 3, it's gonna be equal to 1, right? And for beta, for neutron, you have minus 1 by 3, minus 1 by 3, and plus 2 by 3, right? 2 by 3, you get 0. So neutron has no charge in this setup, and for the proton, it has 1 charge from the calculation of each quark component. Okay. Yeah, the beta plus decay is decomposed into neutron, right? Proton turns to be neutron, and the positron is emitted. Okay, positron is emitted, and together with the positron, this is E plus. Okay, it is the antiparticle to the electron, but it has positive charge. And you get also the neutrino, which is a very, very small particle compared to electron. You could see that electron is already very small compared to the neutron or the proton. Neutrino here, electron neutrino, this one is called electron neutrino. electron new new I think yes, electron no, in EU, electron neutrino. Electron neutrino is even much smaller than electron, and the information for this particle is still missing because it's very hard to detect. Okay, and that's the whole process for the beta plus decay. We start from proton, and proton turns to be neutron, and the two particles are emitted, positron and neutrino. Beta minus decay start from neutron. Okay, when the nucleus has too many neutrons. In this case, the nucleus had too many protons, turns to be neutron. But for this one, for this type of nucleus, there are too many neutrons. It's neutron rich. Neutron turns to be proton, and one quark turns to be one down quark turns to be up quark, and we get proton. And during this emission, the electron is emitted. Okay, so that the whole process still remain neutralized. So neutron has no charge. This one has plus, so that's why we get one proton as the outcome. And during this emission, there will be electron emitted, which is the beta minus particle. And apart from this, the missing particle is added, which is electron antineutrino. Okay, they may use the tilde symbol or the bar, it's up to them, but don't worry about it. This is called electron anti-neutrino. Okay, it's the antiparticle to each other. Okay, in more detail in the nuclear particle scale, we won't talk about proton to become neutron. We have to write down up quarks turns to be down quark together with proton and electron antineutrino. And for the beta minus decay process, the down quark, one of the down quark turns to be up quark, and that's why you have two yellow, two up as the output here. Okay, and one of the down quark is turned to be one of the down quark turns to be up quark, and we get the outcome here. And apart from that, the electron is emitted, right, which is this one, and the electron antineutrino is found here. Okay, we write down here. Yeah, this is the expression in in particle physics method, but this one represent in the whole nucleus form, right? Neutron to proton and electron. Okay, in bachelor degree level, the way to understand everything could be expressed by this diagram. Okay, it might be a little bit complicated for you, but anyway, I added to you in bachelor. In high school level. A down quark, okay, from neutron to become proton. This is the beta minus decay process, right? Because we get electron as the outcome, and we get electron antineutrino too. Okay, in the nuclear particle scale, up quarks just go, okay, and down quarks just go, and one of the down quark in neutron. Here, this is neutron. One of the down quark changes itself to become up quark. And how is that? Let's consider the red arrow here. This down quark emitted the W minus boson. Okay, the down quark of the neutron emits a W minus boson. Okay, this one, and later turns to be an up quark. It changes itself to become up quark of the proton, and this the particle now becomes proton, no longer neutron. And the W minus boson disintegrated into electron and anti-neutrino. You could see why the arrow doesn't go out, because this is the anti-mutant and anti-particle. So the arrow is in the opposite way. Okay. Yeah, we got beta particle, beta minus particle, or simply speaking, it's an electron. And we get also electron entry neutrino, which is nu bar with subscript E. Okay, this is the Fireman diagram. Okay, in English they call Fireman diagram. You may know that Fireman is a famous modern physicist. Okay, if you are in love in this subject, you don't need to become a doctor or มีคนถามผมเรื่องอะไร604 ขออนุญาตลาณนนท์ได้ครับณนนท์ชื่อจริงชื่ออะไรผมไม่ทราบมีนบด้วยนบก็ลานะนบห้อง605นบห้อง605นบนี่น่าจะใช้สิทธิ์หรือเปล่าครับนะปกติใช้สิทธิ์จะเข้าที่ใช่ปะใช่ใช้สิทธิ์หรือเปล่าไม่รู้นะณนนท์นี่คือใครไม่รู้ที่จดหมายมา Okay, anyway, don't worry about it. Okay, I just saw it in the group line chat. Okay, yes, the conversion, right? You have seen the Feynman diagram. I don't know whether you know Feynman or not, but anyway, to make the inspiration to you, I'm gonna bring you to Feynman. Fireman, actually, sorry, I pronounced it in a German way. Oh no, sorry for this one. Where is that? This one, right? Okay, Feynman diagram. Richard Feynman. Okay, this is the modern American physicist. Okay, he is a modern physicist. Okay, and you could find his lecture. If you fall in love with particle physics, you fall in love with quantum mechanics, you fall in love with nuclear physics, you have to think about him. Okay, Richard Feynman, Richard Feynman is the person who created the Feynman diagram. Okay, the diagram you have seen before. Yeah, the diagram like this. That's valid for photon, for any particle in standard model. Okay, he has also made a lecture to that. Yeah, this is one of the Feynman diagram. Okay, for the neutron to become a proton. Okay, the process in 63, if you take a close look, which is 63, the complete version already with the electron anti-neutrino. Okay, you take a closer look again. The mass difference delta M, right? Mass difference is denoted by delta M. The delta M could be found from the difference, right? The difference นะมีรุ่นพี่คุณนะที่แบบตกหลุมรักฟิสิกส์ไปเรียนคณะวิทยาศาสตร์เลยก็มีนะแต่ผมว่าไม่ต้องไปสนใจเขาเรียกว่าอะไรต้องไปสนใจกับค่านิยมอะไรเท่าไหร่เราเรียนอย่างที่เราอยากรู้อยากเป็นนะเพราะคุณอยู่กับมันมีความสุขเดี๋ยวคุณก็จะเก่งกับมันนะโอเคไหมมีความสุขกับมันไม่จำเป็นต้องมาแข่งขันกับใครนะครับโอเคไหมyes. Once you take a close look to 63, and now you have already added the missing particle, right? I don't know. Maybe in the future there might be some more particles here, but at the moment the information in the society is the following: they have just only discovered the electron anti-neutrino, and we make the mass difference, the mass of neutron on the left-hand side, right? The input side, and the output side. There are 3 particles, and mass of proton, mass of electron. Okay, now mass of electron could be written in electron volt per c square. Okay, in let's say if we don't know the mass of the electron anti-neutrino, we are going to estimate the or approximate the mass of the electron and neutrino. You need to have a special device to detect the mass of the electron and neutrino, but now it's beyond the ability by human. Okay, but at least human know that electron neutrino exists, but we would not be able to measure its mass right now. Okay, the mass difference found to be 0.789 plus the mass of electron in neutrino. But we don't know what is the exact value for the mass of electron and neutrino. Maybe in your generation, okay, maybe you are 40 years old, 50 years old, and 60 years old, you might be the person who could really get the exact value for the mass of electron and neutrino. Now the people in the physics society believe that the mass of the electron and neutrino is much smaller than the mass of the electron. You know, mass of electron is 0.511 mega. Okay, mega means million. But they believe that the mass of electron in neutrino is not in the mega electron volt. It's only electron volt. Okay, it's 1 million less than the scale of the electron mass. Okay, you could see the scale of the neutron or the proton mass is almost 1,000 greater than the electron, 2,000 greater than the electron mass, but the mass of electron and neutrino is million less than the mass of electron, and it's not 1 eV, it's 1 by 10,000 or 1,000. Okay, it's like 1,000 million less than the mass of electron. Okay, they believe that, but now it's beyond the ability of the apparatus in physics. The mass of electron and neutrino lies in this range, which is very, very hard to detect. And now the released energy is going to be 0.789 mega electron volts. Okay, once you convert it by multiplying it with the c square, right? You get the actual mass in mega electron volt from this process. Okay, 63 release the energy around 0.8 mega electron volt, and for the process with positron, which is beta plus process, beta plus decay, we have we start from nitrogen 12 to become carbon 12. This is the common isotope of the carbon in real world in the nature, and we get positron and electron neutrino. Okay, without bar. Bar means anti-particle. Here, the beta plus process bring us to the normal electron neutrino, okay, not anti-neutrino. The neutrino, which is the word that Enrico Fermi has said before, has the following properties. It has zero charge. Okay, it's neutral. There is no charge to that. A mass is much smaller than the electron, and as you can see here, it's 1,000 million or 100 million less than the mass of electron, which is very, very, very tiny. And the mass is much smaller than electron, but probably not zero. Okay, it's not zero, but it's beyond the ability of human right now. Maybe in your generation, once you are 60 years old or you are senior like me, and that might be the time the physics has discovered the exact value for the mass of neutrino particles. Okay, recent experiment suggests that the neutrino definitely has mass, but the value is not sure. Perhaps less than 1 electron volt per c square. As you can see here, it's less than, much less than 1 eV per c square. Because it's not well known, okay, the information might be different from time to time, from area to areas. But the important thing in physics is that the spin number for the neutrino, whether it's electron antineutrino or electron neutrino, it has the spin of 1/2, okay, in the same way as electron. And the ms number, okay, m with subscript s, the spin number in the previous chapter, is very weak. to detect because it has very weak interaction to other particle, making it difficult to detect. Okay, that's the difficulty. I think it's not beyond the ability by human. We need to wait only. Okay. The positive beta decay cannot occur in an isolated proton, according to this process, because the mass of the neutron is greater than the mass of the proton usually, and you have two more particles. It's impossible that this process is going to take place because the mass on the left hand side is less than the mass on the right hand side. So in order for 68 this process to become true, you need to put more energy to this side, okay, so that the energy is converted to become mass for several particles on the right hand side in 68. Okay, the mass of the neutron being greater than the mass of the proton. The positive beta decay can happen only inside nuclei when the daughter nuclei has greater binding energy and therefore lower total energy than the mother nucleus. Okay, it means you could get this process when the daughter particles are very dense. Okay, the daughter nucleus are very dense. It has very great binding energy. I think you know binding energy, right? You have seen before in the beginning of this chapter is the energy that try to compress several particles, several nucleons together. Okay. The next one is the series. Okay, you have finished beta decay and alpha decay. Now let's talk about the actual scenario of beta and alpha decay. There are four series of possible isotope to emit alpha and beta particles. The first family is uranium-298. Okay, the second one is uranium-235, which is the very useful version, really useful series for human to produce electricity in nuclear power plant. And the third series is it's still uranium, but it's called actinium family. The third series is thorium. Is made by thorium 232, and atomic number is 90. It's no longer uranium, it's thorium. The next one is 93, which is Neptunium. Okay, Neptunium has 237 nucleons. It's a little bit bigger than uranium and thorium, and the proton is much greater. It's a little bit greater. It's 93. They will all end up with the lead, right? This element which has 82 protons, and it stay in different version, which is different isotopes for lead 206, 207, 208, 209. That's the ending point. Okay, and I lead every day in our life nowadays. Okay, you cannot see uranium easily, right? But anyway, it's going to stop as the lead, and human use lead for any other purpose. Okay, the half-life is the major different factors for different families. This is in 1,000 million. Okay, the half-life uranium. You have 2 kilograms of uranium. Once the time goes by 4.47 thousand million year, you will have only 1 kilogram of uranium. Okay, half of the initial element disappear. Okay, actinium has shorter half-life, around 704 million years, but thorium is even longer than the uranium-238. Okay, it's I don't know how to say, it's brilliant, 10 billion years or something like that, and this one is 2 million years. Okay, Neptunium. Okay, the most familiar isotope for us is uranium-238 and 235. And one of the family, let's consider Neptunium, right? Or the thorium-232. Thorium-232 232 has the following decay process. It combines both beta and alpha processes, I would say. Decay with violet arrows toward the lower left are alpha decay. Okay, they change their nucleons by this is 232, this is 228. So they release 4 nucleons. Okay, they reduce their nucleons by 4. So it means helium-42. So helium-42 is the alpha particle. So thorium-232 to become radium-228, this violet one, we got the alpha particle from this root. And once the radium turn to the right, nucleon is the same. But because it's full of neutron, right? Neutron turns to be proton, and we got actinium. Let's go to the periodic table. Where is that? Okay, here. Where is that? Okay, let me open it like this. No. This, no. Okay, and let me open it like this. Okay. Radium-238, where is that? Radium. Okay, radium is 88 right now here. Okay, and it's turned to be, okay, 1 neutron turns to be proton, right? So the number of nucleon is the same, but the number of proton increases by 1. So when the number of proton or atomic number increases by 1, we're gonna get 89. Okay, from 88 by radon, we get 89, and 89 correspond to actinium here. Okay, and once the time goes by, actinium that has 228, still 228 nucleons inside the nucleus, one of the neutron now changes itself to be turns to be proton. So from 89 we got 1 more proton, we got 90 proton. So now the element changes itself to thorium-228. Okay, and now the nucleus of thorium behave in a different way. They turn to be radium-224. They throw away four nucleons, and that's helium-42, right? 2 protons are missing from thorium. So thorium right here, 90 protons, and 2 protons are thrown away. We're gonna get back to radium-88, but radium-88 with 88 protons, right, has only 224 nucleons. Okay, and this is the emission of, oh sorry, this is helium, not hydrogen. And this is the process of alpha emission, right? Alpha particle emission. Now, radium-224 that has 88 protons throw away helium-42. This is the alpha particle again, helium-42. Okay, they throw away 4 nucleons from 224 to become only 220. We get back by 2 from radium to 87 and 86. We arrive at radon 86 here that has nucleon by 220 particles. And radon again emits 4 nucleons are thrown away. We reduce the number of nucleon 220 by 4, and we arrive at 214, and 2 protons are missing during the alpha emission process, right? From radon, we get back 2 steps, right? We arrive at polonium 84, and 84 polonium has 260 nucleon. During not only the final one, polonium still emits the alpha particle. They throw away 4 nucleons. 216 becomes now 212, and 2 protons are thrown away. Polonium has to go back by 2 steps, right? 1 and 2. We arrive at lead, okay, that has only 82 protons, but the number of nucleons is still high for lead in this version. They reduce, okay, one of the neutron in the nucleus of 212 lead turns to be proton, okay? So we have one more proton inside the nucleus of the lead. Where is the lead? Okay, we got one more. We now get one more proton. We have to go forward by 1, which corresponds to the element bismuth. Bismuth 83 that has still the same number of nucleon, 212. This bismuth has 2 ways to go. Okay, the first way is they emit the alpha particle. They reduce the number of nucleon by 4. 212 becomes now 208. And 2 protons are discarded, are thrown away as the alpha particle, right? Bismuth has to go back to the left-hand side by 2 steps. 1 and 2, we arrive at thallium. Thallium 81, okay, that has 208 nucleons. This is the first way for the bismuth to 212. Another way for bismuth 212 is that one of the neutron inside the nucleus changes itself to become proton. So bismuth has one more proton. Here is bismuth. It go to the right by 1. It corresponds to polonium. Polonium here is different from polonium 216 because it has only 212 nucleon right now. The nuclear side is smaller and smaller. Okay, and polonium has the way to go by emitting the alpha particle, reduce the number of nucleon by 4. 212 reduce has to change or throw away 4 nucleons, so it becomes 208, which is and polonium has to go back by 2 because they throw away 2 protons, right? Polonium go to left by 2 steps, 2 jumps, 1, 2. It corresponds to lead 82, and now the number of nucleons is quite low. Right now is 208. Okay. And the thallium too, the thallium that stopped after the alpha emission, thallium is here 81. One of the neutron inside the thallium nucleus turns itself to become proton. So thallium has one more proton. It goes to the right by 1. It reaches the lead 82 and exactly the same number of nucleon, which is lead 208. Okay, this is one example of the family, 4 famous family in our 4 radioactive series in nature. Thorium-232, we arrive at lead 208, okay, which is a kind of isotope of the lead. Okay, for the rest of the remaining 3 families, you could browse the information from any book from internet or something like that. But we don't have so much time. We need to go for the next decay. It's gamma decay. It's not difficult. We have 10, right? We have only 4 minutes left, right? We have only 4 minutes remaining. Okay, anyway, don't worry about it. Yeah. The gamma decay is different from alpha and beta decay. Okay, alpha decay is the big process that throw away helium nucleus. Beta decay is a process that is a little bit more complicated. It's tiny. It emits a small particle. But gamma decay doesn't release any particle at all. It's only high energy photon. Okay. Nucleus undergo radioactive decay that cause. Let me open. No, sorry for that. Okay. Anyway. Okay, gamma decay could take place after the alpha emission and beta emission. Okay, the 2 former processes may take place first, and the gamma process will follow later. However, the daughter nucleus often remains in an excited state, which appear to be unstable. Even the alpha particle has emitted, even the beta particles, whether beta plus or beta minus particles have emitted. Sometimes the nucleus still remain in excited state because there is some vibration for the proton and neutron, so it's still not stable for them, and caused by because there is still vibration caused by proton and neutrons. The nucleus is still unstable, and the way to be stable is that they just released. Okay, once they vibrate, they release the photon, and that photon is called gamma ray. Okay, it's a high energy photon actually. So there is no particle emitted. It's only photon, and photon has no mass, right? But there it is energy, because physics is the topic that concerns energy, right? The typical gamma energy is from 10 kilo electron volt to 5 mega electron volt. Okay, it's high. Okay, it's mega electron volt is quite high, and gamma decay will take place after alpha decay or even beta decay. It depends. For example, in the radium 226 process, we got 222 radon, right? And 86, that's the number of protons because we throw away 2 protons in terms of alpha particle. But the radon nucleus may not stay at the ground state immediately. Is denoted by this star notation. Sorry. It means that the nucleus still stay in the excited state. There is some vibration about vibration for the proton and neutrons inside the nucleus. And in order for radon nucleus to become stable, they are going to release, the nucleus of the radon will release the gamma ray or the photon with high energy. Okay, star represent the excited state of the nucleus. And the total released energy in the gamma process from radon star to radon without star plus the gamma photon, the energy by gamma is from 4.871 to 4.685. Okay, this is the excited state. This is the typical state in 69. Okay, the radium start from here, right? And it can emit the radon. It can emit the radon. If the radon stay in the ground state, they release the alpha particle with this energy difference. But if they release the energy for alpha particle only this amount, the nucleus of the radon still stay in the excited state with star. And the radon in excited state will further emit the energy in terms of gamma emission, gamma particle. You can say, but it's not the actual particle. Okay. The difference between the full released energy for alpha particle and the partial released energy for the alpha particle will be the difference which is the value for the gamma ray energy, which is one here. Okay, the difference of these two values is 0.186 mega electron volt. Okay, for radium process, radium decay, we get the gamma energy in the scale of 0.2, approximately 0.18 mega electron volt per decay. Okay, per process. If you have more, you just multiply this energy. Okay, the time now is over. We are gonna talk about only one page. Okay, let's finish this one. In gamma decay, the mass number doesn't change. Okay, we don't do anything with the nucleus. We just wait for the nucleus to have no more vibration, and during this process, they are gonna release the gamma or the photon gamma ray. Okay, there is no change in mass number A nor atomic number Z. Okay, The for gamma decay that happens after the beta decay is the following. For example, the boron 12 turns to be carbon 12. Okay, but the nucleus of the carbon here is still in the excited state with vibration, and of course this is the beta minus process, right? One neutron turns to be proton, so they are gonna release the electron, and of course for preciseness, to be precise, we have electron entry neutrino whose mass is still unknown nowadays. Yeah, and okay, the other stuff have no problem, but the carbon nucleus that has star, which is still in the excited state, will be cooled down, okay, after the vibration of proton and neutrons inside the nucleus. They will release the gamma ray 2 in 70. Okay, so this is the possible way also for the gamma emission in the beta decay process. Okay, not only the alpha decay like in radon and radium and radon. Okay, so today the time is over, and please don't forget to write down your name. I'm going to capture and send it to our live group in 3 channels, right? No one is in the Streamlab. Today is Friday, right? So we need to have the homework, right? So the homework is something about the beta decay process or alpha decay process. Compute the released energy of the nucleus in alpha or beta decay process. Only one problem. See you on next week. See you next Wednesday. I'm going to create the homework assignment in our Google Classrooms. สวัสดีครับ บ๊ายบายครับ If you have any questions just let me know. Okay ถ้าเรียนตรงไหนไม่รู้เรื่องครับโปรดถามแบบยกมือถามแล้วก็การบ้านเดี๋ยวส่งให้นะครับ ขออภัยขวัตที่เข้าใจผิดเรื่องการตกไม่ตกนะครับโอเคครับเมธาสิทธิ์กับรู้สึกวีรพัฒน์นะอย่าลืมทวงผม1 คะแนนนะครับเนื่องจากออกข้อสอบผิดช้อยผิดนะครับ so บ๊ายบายครับสวัสดีครับ and if you have to export in yeah send it to me there. To make progress. Here. MacBook Pro. I don't understand why we couldn't see. Okay. Here. Oh no. Petra. Right, Petra. And here, Petra. We opened soon to YouTube. Yep. Just open soon to YouTube. Zoom to YouTube. There's no. We need to open also. Yeah. The OBS OBS1. Still is well, right? Still is good. Actual About the CPU stuff. The sound test. I got it. It's all right. Okay. No, the sound here too. It's all right. It's so there. It's still you can't leave it like this. See what's going on. Okay. Panaton. Okay, Panaton M605 has already alive, and now it's the section for good morning, everybody. Let me check whether the sound test 1, 2, 3. Okay. Now it's time for M605 section. We will start our lecture in chapter 7 soon. Nuclear physics and particle physics, right? Now Labipon not Tobin, but Panaton, all right? Other persons to start typing your name. Okay. 2 people are on leave. For M605, we alive somehow the carbon dating. We finished it, the carbon dating, right? And we will start the nuclear reactions. We arrive at the problem of nuclear reaction energy, right? Nuclear reaction energy. Okay. Let's continue our story. Here, before we go ahead with the nuclear reaction energy computation, we will consider a little bit basic equation balancement, or how to balance the equation in nuclear reaction process. Okay, let's do that. We arrive at 87. Okay, now the pages here are still to be increased continuously. Okay, the next one, in this example, which is taken from book number 1, it is example 29.6. It's the basic thing to scale or to balance the reaction process. In 1932 in England, Robert Chadwick bombarded a beryllium. Okay, beryllium, right? Let's open another one in nuclear physics. Close this one and open the one for M605 right here. Let's go to the the table of beryllium, right? I think at the beginning. Here. Okay, let's consider this table. We have beryllium 94. Okay, this one beryllium 94 is one of the isotope. We have also beryllium 84, right? Before we have considered beryllium 84. But at the moment, Robert Chadwick tried to bombard the beryllium 84 by using the alpha particle, right? You know, helium 42. Helium 42 is the nucleus of alpha particle is the nucleus of the helium 42, right? And Robert Chadwick accelerate the alpha particle, but somehow because it's positive charge, right? You can use the magnetic field to increase their velocity, and then you could get the increasing speed, increasing the high speed alpha particle, and this alpha particle is going to crash the nucleus of beryllium 94, which is another type, which is an isotope of beryllium. We have also beryllium 84, right? Yeah. Beryllium 94 is a bigger isotope than beryllium 84, and what Robert Chadwick has done is to accelerate the alpha particle to crash or to hit the beryllium 94, and the outcome of his process is the typical carbon we could find in nature, which is carbon 12. Okay, and one important thing is another particle, and which is denoted by here X. Okay, X is the known, and A is the number of nucleon. Okay, A is the number of nucleon. Z is the number of protons inside the nucleus, right? So the question is, what is the particle XAZ, XAZ? Okay, the X is not known because we don't know which element it is, right? In the reaction process in 79, okay, in this equation, what is the particle X? So how could we solve this problem? ดูที่ซูมก่อนนะครับว่ามีคนจะเข้าหรือไม่นะครับ Okay, no one, right? No one want to join us in Zoom, right? Okay. Yeah, we need to balance that equation so that we could know what kind of element it is, right? Yeah. In order to do this, we need to follow the rule that the number of nucleons remain the same. Okay, even you put so high energy to that, you accelerate the alpha particle and hit the beryllium. Of course, the outcome might have some remaining energy, and they are gonna move due to the kinetic energy remaining, right? To make this process balance it, let's consider the number of nucleons. Okay, the numbers in the upper part of those four elements, those four particles. Of course, we have 4 plus 9 plus 12. Oh, no, sorry. On the left hand side, at the input side, 4 plus 9, which become 13, right? And on the right hand side, it's 12 plus A, right? A is the number of nucleon for the X particle. So we have 4 plus 9 on the left hand side. Okay, that's the number of nucleons. On the right hand side, it's 12 plus A. Okay, 12 plus A means A is unknown, right? The number of nucleons remaining for the X particle. And that's the upper part, which is the number of nucleons, number of proton plus number of proton plus number of neutrons, right? Okay, the next one is the number of protons, that's the atomic number, right? The number that identify which element it is. Okay, we have here on the left hand side, the input side 2 plus 4. Okay, on the left hand side 2 plus 4. And on the right hand side, we have 6 plus 7. We're going to solve these two equations, two variables, two equations. It's quite simple, right? 13, 12, so A is number 1, right? Yeah. 4 plus 9 is 13, and 13 minus 12 is going to be number 1. And 2 plus 4 becomes 6, and 6 minus 6 is 0. So we end up with the particle x10. And what is that? X10 means the number of nucleon. The number of, we have one nucleon remaining. I'm not sure whether it is proton or neutron. It can be either proton or neutron. But at the lower part, 2 plus 4 minus 6 becomes 0. So the number of proton is 0. It means there is no proton inside the nucleus. So we could identify that. Here in the nucleus, the nucleon is neutron. So the result of this process by Robert Chadwick, actually he got the neutron particle. Okay, and that's the way to find the elements, to find the particle from the reaction process. And this was discovered in 1932 by Robert Chadwick. Okay, now it's time for us to take a close look to the energy, right? Because in physics, energy is important, right? Energy is important for us, and let's see what happened. Okay. Yeah. Let's see what happened in this scenario. Oh no. Supersin too. Oh, I don't know. I don't see Supersin in this channel. I'm sorry for that. My God. Oh no. เดี๋ยวนะครับ เช็คชื่อห้อง04หาไม่เจออีกหลายคนอยู่นะครับ เดี๋ยวเขาจะว่าผมนะครับ Oh, where is my mouse นะ Oh my God เพิ่งเห็นเหมือนกันครับพวิทย์เพิ่งพิมพ์มา Oh no, it's better to go by this one. Where's my mouse? Okay. โอ้เพิ่งเห็นว่าพวกสุภสินเขาพิมพ์ channel Steam Lab มา Okay, let me see. Okay. Yes, the nuclear reaction energy, right? It's the Q, right? It's Q. Q could be computed from 931.5 mega electron volt per atomic mass unit 2, right? Where is my mouse? And let me check the channel. Otherwise, the information is gonna missing. It's gonna be missing. Yes, this one. Okay, here. The people like Supersina. Supersin. พวกพิเชษพงษ์นะเดี๋ยวหาชื่อเขาไม่เจอครับ these 3 people from M604. Okay. It's time now for us. Okay. The total released energy, right, from nuclear reaction process. You know that nuclear reaction is the decomposition of the big nucleus. Okay, made by human. Okay, it doesn't happen in nature. Okay, that is the man-made effect. Yes, the process is the following. One example is lithium, right? Lithium is bombarded. The lithium is the second one. Lithium is hit by a proton. Okay, this is the hydrogen nucleus. Okay, without electron. Okay, there is no electron, and you just accelerate the proton to let me write down how it's going. So this is lithium, right? There are three proton, and you have 4 neutron. That's the nucleus by lithium 73, and you accelerate the proton, which is denoted here 1 1, right? H11. It moves in this way, okay? And you accelerate it with high speed, and this process turns to be the product like this, the output like this. Okay, panatat, the process appears to be like this. Okay, the one man you get 4 proton. Oh, so you get two protons and sorry for that. You get 2 neutron. Okay, you get 2 neutron and proton 2 here. Okay, and this one is known as lithium 73, and this one is known as alpha particle, right? Helium 42, right? 2 protons and 4 nucleon. This is helium 422, right? Another piece of helium 42. All right. Yeah, that's the whole thing in this process. It's not difficult, right? You can analyze it by yourself. It's not too difficult. Yes. The lithium is bombarded by a proton, and 2 alpha particles emerged as the product, right? According to this equation. Determine the reaction energy Q. Okay. Yeah. We need to find the mass difference, and then we convert the mass difference to the energy by using the Albert-Einstein relation key E mc², right? But we are going to use the letter Q. The reaction energy. Okay. Yes, we go to the table to look for the mass of helium 11, which is hydrogen nucleus. Mass of hydrogen is right here. Atomic mass. Okay, we don't talk about mass number. That's the exact number of nucleon, right? Yes. This is proton, right? Helium 11, 1.007825. That's the mass of the nucleus of the hydrogen or the proton, right? That's the mass of proton. And here's the mass of lithium 73. Where is lithium 7? Lithium 7 means this one. Okay, this is lithium 63. Lithium 73 is this one, and we're gonna take 7.016, 7.016005. Okay, this value. And next one is the mass of helium 42, which is the alpha particle. Helium 42, this is helium 32, this is helium 42. We are going to take this value, pick up this value, 4.002603. But once we have 2 pieces of the particle, we're going to have 2 times that number, 4.002673. All right. Yeah, that's the thing we could pick up from the table, okay, if it is available in the table. Otherwise, you need to go to the appendix of the book, okay, which is not too difficult at all, right? And once you get these three numbers, you express it. Okay, the mass actually should be represented in the SI scale, right? Capital M. And we express it in the atomic mass unit. We change the C squared to become 931.5, and the unit is mega electron volt per atomic mass unit, right? Here, everything will be computed in atomic mass unit, and we compute it by 931.5. Okay, the mass difference is not the big deal. It's only 0.018624. And after that, you make the multiplication, you get 13.37. Okay, and you can see that it's in the scale of 10, right? Almost 20 mega electron volt. It's quite high. Yeah, it's of course the helium, once it hits the lithium, they're gonna have more kinetic energy by 17.35. Okay, of course, at the input side, they may have kinetic energy because this one is moving with speed, with high speed v. Okay, with velocity, with speed, so the kinetic energy exit for some value. But after the crash, after the decomposition here with two pieces, these are alpha particles. Both alpha particles will have kinetic energy greater than the input kinetic energy here, because the energy difference from both sides, from input and output, becomes positive. So this one have more. Oh no. You would need to insert more. The kinetic energy is reduced, not increased. Okay, these two alpha particles have less kinetic energy because the left hand side is greater, right? So the released kinetic energy here should be less than the kinetic energy at the input side. Okay, and after bombardment in 84, the total kinetic energy of the two separate particles is greater than. I don't understand. Yes, because the mass is greater, so the mass turns to be energy. That is correct. I'm sorry for that. The kinetic energy should be increased by 17.35 because the mass is converted to energy. So it's already correct. I'm sorry for that, to make you be confused. โอเคขอโทษนะครับก็คือพลังงานจนจะมากขึ้นนะเพราะว่าแมสมันลบออกมาแล้วเป็นบวกใช่ไหมก็มวลก็จะเปลี่ยนเป็นพลังงานให้นะครับ Okay, sorry for that. Okay, the initial total kinetic energy which is caused by the proton and the lithium nucleus here. This is the initial kinetic energy, which is the part by proton. Okay, and if lithium is moving, it would have also kinetic energy. But anyway, after the bombardment, after the calculation, we find that the mass difference is positive, so the released energy should be also positive then, and the summation of the kinetic energy of these two particles should be greater than that one on the left hand side. And now we move to another type of the reaction process. We move to the next type of the reaction process. It is the process by Rutherford, right? Rutherford is the person who considered the reaction the nuclear reaction process. This is the gamma decay carbon dating. Here in 19 19, Rutherford has made the experiment, right? He accelerated the alpha particle. This one too, right? This is the accelerated proton by Ludwig Chadwick, right? Yeah. No, Robert Chadwick is helium too. This one from someone else. They accelerate the proton to hit the lithium nucleus, but for Rutherford, he accelerates the alpha particle to hit sorry, to hit the nitrogen 14. Okay, nitrogen 14, and the outcome is oxygen 17. Okay, it's not oxygen 16. Okay, and together with proton. Okay, and yeah, let me write down what happened in Rutherford experiment. Let me write down what's going on in Rutherford experiment. Okay, in Rutherford experiment, he has alpha particle, which is helium 42, right? 2 protons. And neutron like this, and this alpha particle is accelerated. Is accelerated with speed v, and it hits nitrogen 14.7. So it means we have 7 proton. 7 proton, right? And 1 more proton, and we have 7 neutron. That's the nucleus of nitrogen 14.7. And we have 4 here. We have 6. Oh, sorry for that. We have 6 neutron, and we have 1 more neutron here. Now we have 7 neutron. This is the nucleus of nitrogen. Nitrogen 14. Nitrogen 14.7 is over there, and helium 42, which is the alpha particle right here. It is accelerated, okay, and it goes to hit, or in terms of nuclear reaction, it's called bombardment, right? And the outcome is we got oxygen, right? We get oxygen. There are 8 protons. There are 8 proton. 8. Okay. Oh my God. Okay, 8 protons. 8 proton and 9 neutron. Okay. Yes, 9 neutron. 1, 2, 3, 4, right? 1. Oh no, 1 neutron. Okay, now 7, and here is 2 neutron. No, 2 neutron more. That's the oxygen, right? Oxygen 17.8, because we have 8 proton, 1, 4, 4, right? Number of neutron 2, 4, 6, 9, right? Okay, and we have another one, which is the proton, right? Here, proton. It's a single proton. Okay, and both could move. Okay, if they have enough remaining energy. Okay, This is the product by the result of the experiment by Rutherford, and find the reaction energy for the Rutherford experiment. So we are going to compute the mass difference, right? Mass difference by on both sides. So this is particle A, this is particle B, and mass particle C, and mass particle D, right? We use that formula. We use the reaction formula. Where is that? Here in 83. Okay, we're going to use this expression, and what we found is the following. Of course, mass of helium-42 could be found from this table. Where is that? Here, this table. We start from the first particle. The first particle is mass of helium-42, which is alpha particle, right? Helium-42, this one, okay? Helium-42, I'm not sure whether you could see it. Helium-42 is this one, okay? 4.002603, this one. Okay, we pick up the mass of the helium-42. The next one is nitrogen-14. Nitrogen-14, where is that? This is nitrogen-14, this is nitrogen-15. We are not gonna pick up the nitrogen-15 atomic mass. Okay, we will bring the nitrogen-14, okay, which is 14.003074, this value. And after that, the next element is the oxygen-17. Where is that? Nitrogen-17. We need to find a case when number of neutron is 9. Okay, number of neutron is 9, which is this one. Okay, oxygen-17 has the mass of 16.99 and 132. Here, 16.99, 132. And the next one is the mass of the proton, right? Proton is actually the nucleus of hydrogen-11, the basic element. Okay, so where is that? We go to the basic hydrogen atom, and we have here 1.007825. 1.007825 is left there in the computation. And after that, we make a subtraction, right? 4 numbers, 2 positive numbers and 2 negative numbers. Okay, we put it into the calculator. Okay, you cannot neglect the digits here. Okay, this is very important for physics at the moment. Okay, and then you have to multiply it by 931 because you can also calculate in the SI system, but it's difficult. Okay, you have to take into account 3 times 10 to 8 and square. But for us in we have already prepared everything in the atomic mass unit, right? So C squared becomes 931.5 megaelectron volt per unit, atomic mass unit. And once you get the difference, now it turns to be negative value. What is that? It turns to be negative value. It means the outcome may have less kinetic energy than the input side. Okay, and once the difference, the mass difference is negative, it's no problem. Okay, then we still multiply it by 931.5 megaelectron volt. Whatever amount you obtain from the mass, okay, you get it like this in terms of energy. Okay, and one important thing for the Rutherford experiment is that the energy turns to be negative value, which is different from the previous one. Okay, in the previous one we have 17.35. Okay, the mass difference is positive, and the mass difference turns to be energy as the output. But in the Rutherford experiment, the output energy is negative. What does that mean? It means there will be no kinetic energy emerged from increasing kinetic energy from this process, but the kinetic energy at the output is going to be reduced by 1.192 Okay. Yeah. In conclusion, in these experiments by Rutherford, the kinetic energy is absorbed in the process by 1.192. So the emerging particles, two things here, may have less kinetic energy than the input side. Okay. Yeah, that can happen. Okay. Then the Rutherford reaction will take place if the total initial kinetic energy is at least, or if you need to accelerate the alpha particle with at least this amount of energy. Okay. If you accelerate the alpha particle less than with less energy than this value, this process will not gonna take place, will not occur at all. Okay, because we need at least 1.192 from the EMC square formula. Okay. Yeah, that's the two examples in nuclear reaction. And yeah, the process by Rutherford is endothermic. Do mean down, right? The negative value for the kinetic energy. Endothermic reaction will not occur unless you accelerate that particle with at least this value. Okay, so that they can have enough kinetic energy, and this kinetic energy will be absorbed to make the composition like this. Okay, the incoming particle has at least enough kinetic energy. Okay, you need to accelerate the particle with at least that amount of energy, and once you have enough sufficient, or once you have enough kinetic energy, it can break down the process and it overcome energy deficit. Okay. Now we arrive at the nuclear fission. Where is that? The nuclear fission, right? We are somewhere here. Okay, we have finished it. Nuclear reactions. If you have any questions, just let me know. Now we move to the next one, which is nuclear fission. Okay, this is the long story actually. And then we reach nuclear fission. Okay, which is a more clean energy than the fission, nuclear fission. But nuclear fission is in the former state, right? In our grandparents, in my grandparents' generation, or in your grandparents' generation too, I'm not sure, but it took place so many decades already, nuclear fission. Okay, nuclear fission is a decay process that is also man-made. Okay, it doesn't take place in nature. This is the process done by human, okay, for some specific purpose. Okay, one of these is the war. Okay, I would not recommend anybody to do that. But the good thing is that human has developed or used this process for something good too, right? For example, we use the nuclear fission to produce electricity. That's in the nuclear power plant. Okay, it's good, useful to everyone. Yeah, nuclear fission is the decay process in which unstable nucleus split into two fragments of comparable mass. Okay, you're gonna see that one big nucleus is separated into two big nucleus, and those two big nuclei will be further converted to another generation of the nucleus or nuclei. Okay, and in some cases, it's split into two big nuclei, right? Those are called daughter nuclei. And in this decay process, human can get a lot of energy from that. And in such a reaction, the total mass of the product is less than the original mass of the heavy nucleus. So it's good because the mass difference is positive. Once the mass difference is positive, it means the mass difference is converted to become energy. And Yes, we get the energy from this process, and human has used it for special purpose in a good way. Okay, fission was discovered in 1939. Okay, almost 100 years ago. Okay, by Otto Hahn and Fritz Strassmann. They are physicists, and he made the experiment by bombarding uranium-235. You know that uranium has many isotopes. Actually, it's a big element, right? Because they have 92 proton. It's a big element, actually. Let's take a look at the table of periodic table. Uranium 92. Okay, uranium is over here. It's a big element, as you know. Just apart from this, we could have also element, but they are not stable. Okay, even uranium is still not stable. They have half-life like 1,000 million years and billion years, so on. Yeah, uranium-235 is an isotope of the uranium, and is quite popular to nuclear fission process. These two physicists accelerate the neutron, and the neutron hit the uranium-235. Okay, and of course, once you increase one more nucleon, the nucleus gets stuck. The nucleus get bigger. Okay, the size of the nucleus is bigger, but it stay in the star notation. What does that mean? It's in the excited state. Okay, because neutron has energy, and the nucleus of uranium, of course, the nucleus is bigger by one, right? The neutron is attached to the nucleus, but the whole nucleus is vibrating because in the star process is in the excited state. But once the times go by, it's very short. Okay, uranium. Oh, it's stupid. This one should be 236, not 235. I'm stupid. It needs to be number 6. Okay, not 5. 236 is an intermediate state. Okay, it's in the excited state. There is vibration of proton and neutrons inside the nucleus of uranium-236, and it will last only 10 to 12, 10 to negative 12. So 1 femtosecond is very, very short. Okay, I believe I really appreciate how the physicists measure the fastness by 1 femtosecond. It's really hard. Okay, yeah, X and Y are the daughter nuclei splitting from 236. Okay, and it's known as X and Y are known as fission fragment. Please note that I didn't write down the mass number and the atomic number here. Okay, for both X and Y, because X and Y could be many combinations. And one more is the number of neutron. Okay, neutron is N10, right? And Nn means the number of neutron that emerges from this process. N could be any integer, 1, 2, 3, 4, 5, 6. Okay, this N here, N is the number of neutrons. And now we arrive at the picture version of that equation. Okay, this is the mathematic chemical expression, right? Or nuclear expression. We accelerate the neutron, but with not so high speed. A slow neutron approaches the uranium-235. This is the nucleus of uranium-235, which is an isotope of uranium. The neutron is absorbed by the neutron just stay inside the nucleus. Okay, and it is absorbed by uranium-235. It becomes uranium 236 with star, okay, and yeah, uranium star means it remains in the excited state. And once the vibration is quite strong and strong and strong, the nucleus deforms itself to become like a liquid drop or water drop like that. And yeah, because when there is vibration, the nuclear force may not be able to hold every proton and neutron together anymore. So they are gonna try to leave each other. Okay, if you are close to this, you try to go with this group. If you are close to this, you may go to this group. Okay, that's the way how the proton or neutron make a decision. And the nucleus they form like oscillate in the liquid drop, and after that they really tear apart. Okay, they really are separated from each other, and one of the some few of the neutrons will be separated also from the big nucleus, and the two groups now turn to be group X and group Y. Okay, that's the nucleus X and the nucleus Y. Okay, two lighter nuclei from several neutrons. This is the process of nuclear fission. Okay, according to this topic, and if that could be denoted by this equation. So what are X and Y daughter nuclei? What are the possible nuclei? Because I didn't go into the detail what X and Y are, right? What is the element X? What is the element Y? The physicists have tried to collect the data from experiment, and here is the result. A means the number of nucleon inside the nucleus, right? And they found that this is the mass distribution of the fission fragment. Okay, X and Y. Let's say if this is X and here is this Y, there is high percentage of the nucleus to get the nucleon for X like 95. There is high percentage for the second particle that has nucleon as like a 138, 37, or in this region. Okay, in this region we have more percentage to get X and Y as the combination for that. Okay, so it depends on your protons. Okay, then we can identify X and Y. Okay, we can know the name of X and Y, but according to the measurement results in terms of number of nucleons, we have two possible regions like this for X and Y. And เราต้องจบที่เท่าไหร่11เท่าไหร่ครับ11:30นะ okay, still 30 minutes more. Typical reaction for this type, the typical possible combination for this type is beryllium 141. Okay, beryllium 141 is somehow here. Okay, beryllium 141. This is 140. 141 is somehow a little bit to this, right? 141 nucleon, and we get 56 barium. Number of proton remains 56. Where is that? 56. No, 56 is here. Oh, sorry for that. 56 barium here. Okay, 56 barium here. And we got a second daughter nucleus, which is krypton. Krypton has 36 proton. Where is that? 36 proton. 36. Here, krypton. Krypton and barium. 56. Right. Barium and krypton here. Okay, in the periodic table. Okay. Yeah. we accelerate the the neutron to hit the uranium-235 isotope, and the nucleus try to separate from each other, and finally, due to the high vibration, we get barium and krypton, right? And some of the neutron will emerge also from this separation of nucleus, from the separation of this nucleus. Okay, yeah, barium 141 and krypton 92 are the fission fragments. Okay, not only three particles, we get also the energy to these three components, right? In now we are talking about the reactor, right? Reaction process from the previous section, and most reactors in operation today also use uranium as fuel. Okay, the most popular fuel is uranium, but uranium in nature contains several isotopes. Okay, once the Earth is formed up, we have already got the uranium on Earth. Okay, and we could not do anything. Most reactors in operation today use uranium as fuel. Natural uranium contains 0.7% of the uranium-235. Okay, uranium-235 exists in nature only 0.7%, which is very tiny, right? Tiny portion, less than 1%. Okay, and the remaining, which is 99.3%, is uranium-238 isotope. So yeah, what could we do? But the one that is useful in nuclear fission is this one, okay, which is a rare isotope from the natural uranium. Okay, the 238 isotope of uranium can absorb the neutrons, but it's going to become uranium, the bigger uranium, okay, 239. Yeah, 239 isotope instead of something else, okay, with a bigger nucleus, okay, and it doesn't have enough property to sustain a chain reaction by itself. Okay, it may hit 238 and you can get some energy, but there is no other neutron to hit the next 239 uranium isotope, so they will not take place automatically. You have to inject neutron one by one 239 so that you can get 213. You have to project neutron to uranium-238 all the time so that you can get uranium-239. Okay, but the fission process to produce electricity will take place automatically. Okay, and yeah, the uranium-238, which is the major isotope of uranium, tends to absorb the neutron, but it doesn't go to uranium anymore. It turns to be Neptunium. Where is that Neptunium? This one, okay, to be Neptunium, bigger one with one more proton, and this one to plutonium. What is plutonium? This one, okay, Pu plutonium, I think. Yeah, to the next elements like this. Yeah, that's what we could. Is that correct? Otherwise, I'm gonna bring you to something wrong. Yeah, this plutonium, Pu plutonium. Okay, uranium absorbs neutron, and then some neutron turns to be proton by 1 or by 2. We get Neptunium and plutonium. Okay, and that's the way that take place with uranium 238. Okay, when you insert more neutron, they're gonna change the neutron, will change itself to become proton, and that's why we get bigger element like Neptunium and plutonium. But let's pay attention to only uranium-235 because this is the isotope that could take place automatically without any further feeding neutron to that. Okay, that's the nuclear chain reaction. That's why we say it's automatic process. It's chain process because in each disintegration process there are some emerging neutrons. Okay, one incoming neutron causes a fission event in uranium-235. Okay, uranium-235 is a major fuel for us. Okay, yes. Okay, let me see what's going on to this. Okay, no one is watching. Okay, yes, uranium-235 is the major fuel for the automatic chain reaction, or it's called automatic reaction, or it's called chain reaction. Right? Yes, one neutron, okay, with speed cause a fission event to uranium-235, and as you know, we could get barium-141, krypton-92, right? Barium-141 and krypton-92. And after that, there are few neutron emerges. Some from the measurement, they say that in statistical way, there are approximately 2.5 neutron per process. That's the average value, okay? Because this take place with million nuclei, okay? It's not only one piece of uranium. Okay, several neutrons from the initial fission event cause fission to additional to uranium-235. Okay, you have this one can hit other particle too. Okay, the neutron may hit this one. I don't know. The uranium. No, it's the uranium, but it may not turn to be barium or krypton. It could be any other daughter nuclei according to this distribution. It may not be barium and krypton. It could be in any combination of the dot points here. Okay, the black points here. For example, SR, what is that? SR and XE 95. No, what happened? 95. I want to see 95. Where is that? 95 is no. SR. What is that? SR. Any of you who know SR? SR is here. It's strontium. Okay, strontium. Is SR and XE, I think. Yeah, XE xenon, I think. Yeah, XE xenon. This one is inert gas, right? It's stable already. Okay, XE is stable, but strontium may not be the case. Okay. Yes, and other components of X and Y, right? And during this process, they will also produce neutron, and neutron will hit the next uranium, and we get another pair of daughter nuclei, and this is the second round of neutron creation. And once it creates the neutron will hit the next uranium-235, and we get again the separation of two daughter nuclei like this. Okay, whether it's barium, krypton, strontium, and xenon, or another pair of daughter nuclei according to this distribution. All right. Yeah, that's the first figure. ผมขออนุญาตเข้าห้องน้ำนิดนึงนะครับ The first picture about nucleus decomposition for uranium-235 ขออนุญาตเข้าน้ำนิดนึงOkay, I'm sorry for that. Yes, the uranium-235, right, is the major factor for us in this story. Uranium, uranium-238 is not the big deal, okay, because it's not important isotope. Okay, only uranium-235. Okay, that's the picture from the book number 1, and here is the picture from book number 2. It's in the same way, right? Okay, there are many generations of neutrons. For example, we start from the first generation of the neutron. It moves with a speed, and it hits the uranium-235 again. It's separated into krypton, right? The fission fragment, the first fission fragment, the second fission fragment, which is barium, and krypton and barium, as you can see here. That's the typical pair of daughter nuclei. Krypton and barium. Now we got more here. Krypton and barium moving. We get also the neutron, and some of the neutron doesn't hit anything. It just lost. Okay, and some of the neutron will hit the uranium and uranium-235 again, and it produced like Rb. I don't know. Sr. Okay, strontium and xenon, right? Rb. What is that? I know Cs is cesium, right? Rb, this one. Rb is rubidium, okay? Rubidium. We could get any combination of that, rubidium or cesium, and strontium and xenon too, right? And here is the second generation of the neutron, right? Here is the third generation of the neutron, and it will hit the next uranium-235, and we could get cesium, rubidium, barium, krypton, rubidium, cesium, xenon, and strontium, and we will get further neutron, and they will hit the next round of uranium-235. Okay, and the process will be said in the chain way, right? It's called chain reaction, and this is the nuclear fission. So we say nuclear fission chain reaction, taken from book number 2. And the property, let's get into the detail. It takes place like a random process, right? There are many samples that take place, so we cannot count it one by one. We're gonna use the property idea to that. Okay. Yes, the property of neutron that absorb, the property of neutron absorption by a nucleus is much greater for low energy. Okay, your neutron should not have too or high speed. Okay, if the speed of the neutron is too great, they are not gonna hit. They are not gonna be useful to the next uranium. The slow neutron will start the disintegration of uranium-235. Okay, for high energy neutron like 1 mega electron volt, this is the high energy neutron in mega, right? Million, greater than 1 electron volt, will not be useful to the next uranium. And for uranium-235, the slow neutron will be useful, okay, to cause the next round of fission than the fast neutrons. For the chain reaction to continue, the neutron must be slowed down. Okay, even you get the high-speed neutron, you need to do some technique. You need to use some technique to reduce the speed of the neutron. Okay, and it's not beyond the ability of the human, right? It's not beyond the ability by human, right? Even in nature, the neutron is created with high speed, but it's not beyond our ability, right? Yeah. The way to do is the following. The emitter neutron could be slowed down by collision with nuclei in the surrounding material. For example, a moderator. Okay, it's called moderator. There are many ways to use moderator. You could use like graphite. Okay, graphite is made of carbon, right? And in carbon we have 6 protons, 6 neutron, right? Carbon 12, carbon 14, something like that. And yeah, it's a piece of object, right? And if you want a liquid form, you can use the heavy water. What is heavy water? heavy water means you use the deuteron. You know deuteron, right? Hydrogen is made of 1 proton and 1 neutron, but deuterium is made of 1 neutron, 1 proton, and we have 1 proton, right? So there are 2 nucleons inside the isotope, the second isotope of hydrogen, which is denoted by letter D here. This is the deuteron. We combine deuteron to oxygen. We got D2O, which is the heavy water. It's known as heavy water. Okay, because the nucleus is bigger, it can absorb somehow the speed of the neutron or the high-speed neutron, so that we could control the energy of neutron, so that the neutron will be useful for the next round of fission, together with the uranium-235. Okay, yes, the structure of moderator could be somehow like this. Okay. This is the cross-sectional view of the reactor core that is used in reality. This is developed by human, okay? This is the control lots, okay? And here is the radiation shield, okay? You need to shield, otherwise you get so many particle radiation from the whole process. Yeah, it's harmful to human and everyone, okay? Yeah, we have fuel elements. That's the bar of uranium-235. Okay, and we have moderator material in terms of graphite or heavy water. And as I told you, heavy water is made of deuteron. Deuteron together with oxygen, right? We get D2O, which is a kind of water, but it's not water for drinking. Water to cool down the whole process here in nuclear power plant. Yes, this reactor has the control lot. Okay, if you wanna make the fusion more, you need to leave or have less control lot where to protect. The reactor core contains the control lots. This one, okay. The fuel element. Okay, the red one, fuel elements that contains uranium-235, and moderating material. Moderating material is this one, to control the fission process rates. Okay, so that there will be no too many neutrons inside the system. You can control the number of neutrons by using moderator material. Okay, the rate of reaction is controlled by inserting or withdrawing the control lot. Okay, if you want more, just take out the control lot. Okay, so that the process will take place easily and neutron will flow around the whole area here, and then you have more fission rate. If you want to protect, you don't want to create too much energy, you have to protect the neutron somehow. Okay, the controllers are often made of cadmium. Okay, cadmium. Why? What is the reason why they use cadmium? Because the nuclei of the cadmium can absorb neutron without any additional reaction. Where is cadmium? We use cadmium for that. Oh, I don't understand why. Cadmium. CD cadmium, right? CHCCM cadmium, where is that? CD. I don't know. Where is cadmium? There. D here. Okay, cadmium. Cadmium is a transition metal. Okay, we use cadmium in this application. We use cadmium for control lot. Okay, the brown one, the gray one here is made of usually cadmium, and the nucleus of the cadmium can absorb the neutron without any additional reaction. Okay, in a nuclear power plant, the fission energy appears as kinetic energy of the fission fragments. Okay, that's the main main source of energy we use in nuclear power plants. Okay, we have to thank the physicists and the scientists to create these things. Okay, let's get into the nuclear power plant detail. You have the control lots, which is this one, the gray one here. Okay, control lot to control the rate of the fission process, right? Move it up, you will have higher rate. Lower it down, you will close or reduce the fission rate, right? Because you use cadmium to protect the neutron motion. Okay, and reactor core moderator. Okay, this is the you could use inside this. You may use the I don't know, the heavy water or graphite. Yeah, the this one could be made of of graphite and so on, right? The reactor core, right? This one, okay, that's the substance that reduce the neutron energy, neutron speed, right? Okay, we use the water here inside this one because after the fission, there is energy releasing, which is the kinetic energy of something, right? Of the daughter nuclei or the fission fragments. And once the fission fragment move with energy, it's gonna release the energy, transfer the energy to the water, and water is hot, and now water is flown through this pipe. Please note that this is the special water. We don't let the water to touch any water inside the steam generator. This is the part of mechanical engineering or electrical engineering. Okay, the water of the nuclear plant is separated from the water in the steam generator. Okay, we use the hot water that absorb the energy from the fission fragments flow around this one. Okay, the energy is now transferred to the water. The next portion, the next group of water, and we use the pump here to let the water flow. Okay, and the water gets the heat. This is the second part of the water. They don't touch each other. They are not mixed to each other. And this is the pure water. Pure water is heat up, okay, until it reaches like 600 or 700 degrees Celsius. It is the high energy gas state of the water. It's known as steam. Okay, once the steam is passed through this pipe, it's gonna repel the blade in the turbine. Okay, this is the turbine, and the turbine is attached to the shaft. The shaft is long straight away connected to the generator. Generator is the device that has copper winding, and there is induced magnetic field. And once the copper rotates in the magnetic field, it's going to generate electron movement, and that electron movement will cause the electricity or the current flow. Okay, and we could get electric power. Okay, and that's the selling part of this power plant. Okay, they sell the electricity to people. And let's go ahead with the other components in the nuclear power plant. There is steam, right, which is in the scale of 600 or 700 degrees Celsius. Will flow further. Okay, it's a little bit cooled down, and the steam will be condensed to become another round of water. And we use the steam with low pressure to absorb the heat of this steam. Okay, so that the gas state or the steam version of the water is condensed to become the liquid form of water. Okay, and we use the pump a little bit to move it around to the next boiling process. Okay, and that's the whole thing for the nuclear power plant. Okay, this is the primary loop. Okay, please note that this is denoted by the red color. It means the water here is in a very high temperature, and in the second round, this is the clean or the lower loop of water. It is controlled to touch the blade of the turbine in the steam turbine machine. Okay, that's the schematic diagram of the nuclear power plant. This is the simple version. Actually, there should be some units that takes control of the safety or the security of the power plant, and the time is over now. For M605, right? This week, you need to compute something about nuclear reaction energy, which is this one. Okay, this formula. Oh no, you have to do something about carbon dating or nuclear reaction energy. Okay, let's say homework for M605 today is 21, right? 31.01.02022. Homework is carbon dating or nuclear reaction energy. Nuclear reaction energy. Okay, those are two possible topics that you could choose as the next round of homework, and we're going to see what happened, whether you can understand what I said to you or not. Okay, so it's time to capture your appearance in several channels in YouTube, but no one is in Zoom, right? No one attend class in Zoom. Okay, see you next week. Bye bye ครับ สวัสดีครับ